first of all, I would like to thank organizers for giving me opportunity to present our work in this forum. And the topic is the impact of process integration issues on 0.25 micron GaN HEMT, and my area of work is basically confined to depletion mode HEMTs and mainly for RF application. So the outline of my talk is, I'll start briefly with the significance of GaN semiconductors. Although most of the audience is familiar with this, then what applications and what is the motivation, then what is the market forecast in the recent past, then GaN HEMT technology, why it is very important, then what device development approach we are following at our place, and then the HEMT process sequence we are following, and what are the integration issues we have addressed, and then as we are working for high frequency applications, so as you go up in the frequency, parasitics become very critical. So there are different techniques to reduce those parasitics. So those I will be briefly touching. And then backside process, since it is a gallium nitride over silicon carbide being second or third most hardest material, so backside process becomes equally difficult. So that how we are working on that, and then what are the recent developments going on world over, and then I'll summarize my talk. So to start with, if you consider silicon technology, the most of the advancement in silicon technology have taken place because of process innovations. Newer and newer processes have been developed and technology has advanced, and as on today we are talking about 2 nanometer or 3 nanometer node, whereas in compound semiconductor, specifically in gallium nitride or gallium arsenide, the innovations are mainly material innovations. So technology has advanced because of the material innovations. So material is very critical here. So unless you have a good material, you will not get the desired performance. So material is very critical here. Then for the benefit of the students, I'll just briefly give 2 figure of merit for high electron mobility transistor. It is a 3 terminal device. Source and drain are ohmic contacts, and gate is a Schottky contact. So and a negative voltage at the gate induces a reverse bias and controls the flow of current between source and drain. So very small change in gate voltage induces a large change in source drain current, and that is how we get the high transconductance out of this device. So the figure of merits are mainly cutoff frequency. Cutoff frequency is the frequency at which my current gain is unity, and it is a function of your gate length. So smaller is the gate length, higher is the cutoff frequency. That is why we are going for smaller and smaller gate length to achieve high frequency performances. And then Fmax. Fmax is a figure of merit. It is basically a frequency at which your power gain is unity. So these two are the main main criteria to define how good a device for a particular frequency operation. So just briefly I will discuss the importance of GaN, because it has got better semiconductor device properties in terms of power density, in terms of band gap, in terms of mobility, saturation velocity. So they give advantages over conventional technology of gallium arsenide of power density, size, weight. So you can see that, and at the same time you get very high breakdown voltages. So you can extract high power out of this device. And if you consider the heart of any communication system, that is trans-receive module, for gallium arsenide technology, it is a multi-chip module. You can have almost 8 to 10 MMICs for a particular TR module, whereas with this gallium nitride technology, we can go only to 2-chip TR module. One this GaN based front end TR chip and silicon germanium based core chip. So these two can drastically reduce the size, and This makes them very suitable for airborne radar applications, electronic warfare, missile seekers, then 5G is coming up in a big way, and then power electronics. Although power electronics is mainly dominated by enhancement mode devices, and then satellite communication data link. And if you can see that this frequency spectrum below 3 gigahertz, there are many competing technologies, but above 3 gigahertz, gallium nitride HEMT technology is completely dominating the complete spectrum. So, I worked for a place where we are mainly working for high frequency communication or radar applications, developing GaN HEMT based devices and MMICs. To briefly look at gallium nitride R&D initiative in India, a lot of places are working on this. HEMT technology is being explored at various institutes, and HEMT MMIC technology is as far as to the best of my knowledge, only 2 places are presently working, that is IIT Mumbai and SSPL for our high frequency communication applications. And at my place I am working on 2 gate lengths, 0.15 and 0.25 micron for X and Ku band application. And if you look at international status, mostly the technologies available till 2019 or 20 were 250 nanometer based, and in 2019 UMS and a few other foundries have launched this 0.15. So, now it is in commercial market up to Ku band, and India is doing fairly well in because so many institutes are working, and if you look at in terms of publication, India is 5th because of very good publication. So, very good human resource exists. Now it is high time we should have our own foundry. So, government is seriously thinking about this, and maybe in near future we will have few compound semiconductor foundries meeting the demand for Indian requirements. There is some problem in the figure. So, I just wanted to show you in this slide that at SSPL we started this program in 2008, and our ultimate aim was to develop the MMICs mainly for power amplifier, low noise amplifier, switch applications, and then convert it into a TR chip. And as on today on 23, we have our own PDK almost released, and we have now our own MMICs, and last month only we have tested our first MMIC meeting the designed specification. So, I will share the results also. So, the approach which we are following for RF HEMT is you have to have a concurrent approach, because there are several factors which are very important for RF performance of a device. So, the HEMT structure or the L-GaN, GaN, or whether aluminum indium nitride or GaN HEMT structure is very critical. So, you have to simulate and design that depending on your frequency requirement. Then gate engineering, because gate length is one of the important criteria, but the capacitances associated with gate structure are equally important. And then source drain are very critical, because they are ohmic contact. So, they should offer minimum of the resistance. And then low parasitic interconnection techniques, and mainly the techniques for metal crossovers are air bridge, and for source ground interconnections are via holes. So, these techniques are very essential to achieve high performance devices at X or Ku band. So, reducing gate length may not suffice, but overall device design in terms of layout and layer structure is equally important. If you look at the market forecast, you can see that from 2020 the $891 million business is now projected to reach 2.4. This I am talking in terms of only RF applications, and by 2030 it is completely dominated by gallium nitride on silicon, and gallium nitride on silicon carbide, whereas in silicon, because of the inferior properties to gallium nitride on silicon carbide, silicon is only taking around 1% of the market presently, and projected to reach only 7% by 2026. So, because most of the applications are performance driven for gallium nitride on silicon carbide, so complete market till 2030 is dominated by GaN on silicon carbide. This is because of better material properties one can achieve because of good lattice match with the silicon carbide substrate. So, if you look at the LGAN GaN-HEMT device technology, the main process requirements are, you have to have a material structure growth, and that is done by MOCVD, metallo organic chemical vapor deposition system, or molecular beam epitaxy. Then lithography, it can be optical lithography, it can be electron beam lithography. Then metallization techniques to have your ohmic Schottky and contacts. Then implantation or dry etching to have the device isolation, and then dielectric deposition. This is very critical here, with gallium nitride being very defective material, as in the previous talk also the traps are very important here. So, trap can be either surface traps or bulk traps. So, those traps needs to be taken care of. So, surface traps can be taken care of by passivation process. So, passivation is very important. Once you are done with the device fabrication on front side, depending on your design requirement, you have to reduce the thickness of the wafer. So, here in our case, initial thickness of the wafer is 350 micron, and our all device or MMIC design are for X band are up to 100 micron. So, we have to reduce the thickness of the wafer by grinding. Lapping is not preferred because lapping may introduce defects while you are reducing the thickness. So, grinding is the preferred technique, and that is how we grind our device. And then this since in your power amplifier or low noise amplifier, your source is normally used in common source configuration transistor, the source is required to be grounded. So, source, if you ground it by wire interconnection, it offers inductance, that is at high frequencies, that hampers your gain performance. So, normally source is grounded through via holes. These holes are etched directly from back side of the wafer, and then back side ground plane is connected with the source pad by plating. So, this requires etching or dry etching of silicon carbide. So, these all processes are carried out once you fabricate your device completely on the front side. So, this makes this process very critical. So, one cannot afford to lose wafer at this particular stage. So, back side is very critical here. So, we have done at our place all these processes, and now we have MMICs in place, and we are characterizing them for the desired performance. And what are the challenges for X band GaN-HEMT technology? As I told you, the electron trapping effects. So, these traps, either these traps can be surface traps or bulk traps. Surface traps can be taken care of by your passivation, but if they are bulk traps, you cannot modify their effect by process. So, you have to optimize your growth. And then for high frequency optimization, as I have already mentioned, reducing gate length is not only the requirement, you have to optimize your lace structure as well as your device design. And since we are going for gallium nitride technology, because we can extract high power by applying higher voltages because of high band gap. So, to have very high operating voltage, your gate drain breakdown voltage must be very high, but that is a function of electric field between gate and drain. So, we need to reduce the electric field peak between gate and drain. So, that reduction in peak results in higher breakdown voltages. So, that is normally done by introducing field plates. So, field plates are put in between gate and drain, and peak electric field is reduced, and that is how device breakdown voltage is enhanced. And the normal thumb rule is that your breakdown voltage must be 3 times the operating voltage. So, if you want to operate at 50 volts or 28 volt, your breakdown voltage should be more than 100 volts. Then device performance is again great function of dimensional or placement accuracy. Okay, for higher frequency I may have achieved smaller gate length, but how accurately I am placing that gate in between source and drain is equally important. If normally source, this gate is placed towards source to have very low source resistance, but if you are doing this with electron beam lithography on silicon carbide substrate, the placement is very tricky, and you have to have a very good process control to have the placement accuracy. So, all those things affect your device performance greatly. I will briefly discuss those also. So, this is the material structure we are using at our place, and if you compare this with the conventional commercially available HEMT structure, we are almost matching with that, and this is our system, MOCVD system from Axtron, and presently our buffer layer are carbon doped, whereas this buffer layers are iron doped. So, iron doped buffers are better than carbon doped buffer in terms of traps and high frequency performance. So, now we are in the process of introducing iron in our system to have better performance, but routinely now we at our place we are growing these structures and achieving power of 4 watt to 5 watt per mm at 28 volt. And mainly we are working on two structures, one is thick buffer structure and one is buffer free structure, and in both we have achieved very good control of surface morphology. As you can see that the roughness is of the order of 0.25 nanometer, and step flow morphology is clearly seen, and device performance for both for thick buffer, thin buffer is almost matching. So, this now these two kind of devices we are routinely fabricating. Then other important thing which I mentioned is source and drain ohmic contacts. They are very critical. So, conventionally we were using tie aluminum nickel gold gate, but now we have modified it with tie silicon tie aluminum nickel gold, and this details of this process are published recently in Semiconductor Science and Technology, and now we have 0.1 ohm mm figure of merit for ohmic contacts. Earlier we were getting 0.3, 0.4. So, this source or drain resistance become very critical when you go higher up in the frequency. So, to have high power at X band or Ku band, you need to reduce this ohmic contact resistance. So, you can see that this is our conventional approach in which our surface morphology was also very poor, and the roughness was of the order of 260 angstrom, whereas with this new metal technique we are now 80 angstrom. So, your gate lithography becomes a bit easier also with smooth surface morphology. Then in terms of device design, as I told you that we need to manage the device parasitics at high frequencies. So, source resistance is one of the very important parameter. So, gate is placed slightly towards source to have smaller source resistance and higher gate drain breakdown voltage, but this placement accuracy is very critical. And mushroom gate is normally used. Mushroom gate is used to have smaller footprint that defines the high frequency performance, and the broader head to reduce the gate resistance. Therefore, simulation is very important. So, TCAD simulation is extensively used, mainly Atlas from Silvaco is used to simulate the device performance, and then actual experimentation is carried out. And this slide is just showing you the importance of barrier thickness and gate height head optimization. You see that the cutoff frequency is changing with the gate height. If my gate height is around 1000 angstrom, my cutoff frequency is 40 gigahertz for 0.25 micron. Same with same gate length, if I am increasing my gate head height to 0.2, cutoff frequency is going to 52. So, this is mainly because of the associated parasitic capacitances associated with the gate. So, there are different techniques. This is called gate engineering. By introducing the desired gate T gate shape, you can control the parasitics and enhance the frequency performance. And these are the study of traps. So, one simple technique is to study traps is CV analysis with different frequencies. So, you can vary the frequency and map the capacitance voltage characteristics of the device. So, the first top graph is showing there are traps near your interface of 2DAG, because your CV curve is changing with frequency, whereas in lower it is almost same. So, it is clearly indicating that there are traps in the interface near 2DAG, and this effect you can see also in your pulse IV measurement, where you will see clearly effect of these traps indicating current collapse or knee voltage walkout, knee voltage shift. Coming to the process flow for this 250 nanometer GaN HEMT, we start with source drain fabrication. Then once we fabricate source drain, we go for device isolation either with MESA etching or ion implantation. Here in picture I have shown it with MESA isolation. Then we do passivation. This we call early passivation, because the HEMT characteristic is a great function of your initial surface state. So, you have to preserve the initial surface state of the wafer. So, we do not want to expose the surface to different chemicals. So, we do passivation early and then define gate through electron beam lithography, and we are calling it as a slit, and then etching the slit gates through this electron beam defined dimension through silicon nitride, and then doing second gate lithography to define the head, and then we are going for the metal. So, that is how we are getting our T shaped gate. So, this second lithography step can be optical also, because normally head is around 1 micron. So, it is possible to define that with your optical also, but there the placement accuracy you can compromise, because your electron beam gives you the best placement accuracy. So, once you have defined the gate length of 0.25 micron, then we have to etch silicon nitride. So, second SEM photomicrograph is showing the silicon nitride etched, and our silicon nitride thickness is around 100 nanometer, and then gate metal is done, and this is the gate with the slit, and this silicon nitride etching process is very critical here, because you are bombarded. This etching is normally carried out by plasma processes, and bombardment can damage that gate area. So, your plasma parameter should be selected in such a way that there is no damage on the surface, and that damage can be measured by measuring the source drain current. So, before etching, after etching, you can measure current and see the extent of damage on the surface. Once you are done with this, then this slide shows we are going for now 0.15 micron also. So, this is 0.14 dimension defined in PMMA resist, and then same is etched in silicon nitride, and then gate head is defined and devices are fabricated, and you can see that these are the devices 0.26 micron devices with multiple gates. So, in this gallium nitride technology, you to have very high current handling capability, you have to have multiple gate fingers, and these gate finger, even if one single gate is your bad, your complete device is bad. So, you have to have a very good gate yield over this. And as I told you that gate placement becomes very critical. If you are having very good dimensional control of gate, but its placement between source and drain is not correct, you are going to lose on breakdown voltage of the device, because breakdown voltage is a function of distance between gate and drain. So, in this I am showing that these left side two devices are having very small gate drain distance because of the placement inaccuracy. So, leading to the breakdown voltage of less than 10 volt, whereas the other two devices where my gate placement is correct, my breakdown voltage is more than 57 or 60 volts, and this is before field plate, and this initial requirement without field plate is around 60 volt or 70 volt, and then I enhance this breakdown voltage by placing the field plates. So, field plates, as I told you that the electric field between gate and drain at the gate edge toward drain is maximum, and the order of electric field is around 4 to 5 megavolt per centimeter. So, that is how my device breakdown comes around 50 volt, 60 volt. So, to enhance this you have to reduce peak of this electric field. So, by placing multiple gate fingers, so we can place gate connected field plate or source connected field plate to reduce this peak. So, normally both kind of field plates are used, and electric field peak is brought down to 1.5 to 2 megavolt per centimeter. That is how I am able to increase the breakdown voltage. So, this slide is showing the TCAD simulation. So, you can see that in this, after placing the gate field plates, we have reduced the electric field peak from 4 to 5 megavolt to 1.4 megavolt, and my breakdown voltage has gone above 100 volts or around 100 volts. So, this structures initially we have simulated and then integrated in the device, and then this placement, again this field plate placement very important. In simulation you are getting very good advantage of field plate, but if your placement accuracy is not correct, means the distance between field plate and drain, if it is not controlled, you may not get the advantage. So, that is how we have seen that we have suffered in yield in terms of breakdown voltage around all over the wafer. So, once we have studied and corrected all these things, now you can see that this is the gate, and this is source connected field plate. So, initially we were writing this field plate because field plate length is around 0.6 to 0.7 micron. So, you can write that by optical lithography, but your placement accuracy may be compromised, but now we are doing by direct write. So, this gate as well as field plate we are writing through electron beam lithography, and now we have devices with breakdown voltage greater than 100 volt and giving power 5 watt per mm at 10 gigahertz, suitable for X band application. And in few wafers we have got very poor yield of breakdown voltage. Device RF performance may be good, but your device performance is in terms of breakdown voltage. So, we have done detailed SEM analysis and found that wherever my field plate placement is not correct, my breakdown voltage is less. So, there has to be a minimum distance maintained between gate and drain. It should be more than 1 micron. So, wherever we have got the gate drain distance of 1.4 micron, 3.8 micron, my breakdown voltage is more than 100 volt. So, what I want to stress here is that in spite of the fact that we have designed the devices and simulated the performance, but if my placement accuracy is not correct, I am not going to get the desired performance out of the device. And again this is very simple point that my source drain spacing, my device is designed for 4 micron, but because of diffraction limitation, I am ultimately not printing 4 micron source drain spacing, I am printing 3.8 or 3.6, and when I am placing gate or my gate field plate or source field plate, so I am again compromising device performance. So, first you have to ensure the exact 4 micron source drain spacing. So, we have ensured that initially we made a mask, and once we printed it we used to get 3.4 micron. So, now what we have done, we have biased the mask by 0.6. So, now we are printing 4.6 distance between source and drain, and because of RTP and other diffraction effects, now we are having 4 micron, and that is how we are able to place now gate as well as source field plate correctly. And this is as I told you that there are multiple fingers, and all these fingers are need to be connected. So, by metal crossover. So, metal crossover may be using a dielectric for isolation, but that dielectric adds to stray capacitance. So, minimum capacitance is given by air. So, air bridges are formed. So, this is the process and these are the devices. So, you can see the all other source fingers are connected with air bridge, and this is done by plating, and 3 to 4 micron plating is normally carried out. And we are working on initially we started working with optical lithography 0.7 micron, and now we are working on 3 nodes 0.4, 0.25 and 0.15. And the highest cutoff frequency we have obtained with 0.15 is around 44 gigahertz, suitable for application up to 18 gigahertz. And these are the few of the devices with the multiple gate configurations, and we have now 130 watt also device with 64 fingers. So, this again device complexity comes from the number of gates. Each gate has to be working, otherwise you will not get your device with the desired performance. And this is as I told you, via hole fabrication. Once my complete device is fabricated, I have to grind my wafer and then do backside processing. So, in this I always acknowledge IIT Madras, because this work we started initially, all experimentation was carried out with the help of Professor Das Gupta, and now gradually we have procured the system, and now we are doing same process at SSPL, and this is the via hole from backside, and this is the etching profile, and these are the completely fabricated wafer 100 micron, and all processes are integrated. So, this is source field plate, and this is the via hole from backside, and now we are having these devices giving X band and KU band performance. These are the KU band devices with via hole, air bridge, field plate. So, these all devices we have developed, and then we have now developed a library of these devices, and then models are extracted, and we have a PDK for active component as well as passive component. So, PDK represents the capability of any foundry, because a designer can use a foundry capability by using process design kit. So, process design kit has to be available to the designers. So, this we have released now, and we have designed our own MMICs, and this is the complete fabricated wafer with our own MMICs. 3 kind of MMICs are fabricated here: power amplifier, low noise amplifier and switch. And the main advantage of fabricating over same structure is we can integrate them together to have a TR chip also, because your material structure is same. So, this is the first indigenous MMIC which we have tested only last week, and it is SPDT switch X band and meeting the design performance based on our own PDK. And this is power amplifier, this is under testing. So, we hope to meet the desired results in this also. And these are some of the MMICs. Initially we have gone to UMS and use their PDK and design. So, to gain the design confidence, and we are very happy to see the desired performance was as per our design parameters. And these are few of the research studies which my students are doing. These are the recent publications we have carried out. First is for material structure growth, second is after device fabrication, the effect of traps, how you are going to study the traps, and third is on application of these devices for different radiation effects. And these are few recent studies in which now people are trying to improve the performance of these devices by changing the substrate. Silicon carbide being the expensive substrate, but still there is a scope of improvement. So, people are going for aluminum nitride substrate, because dislocation densities are reduced and you get the better layer structure that gives you better RF performance. So, the best performance reported is 15.2 watt per mm in X band. And then one more new structure people are proposing, because of higher spontaneous polarization. Now, barrier layer is being replaced by aluminum scandium nitride, because it is having almost 30% more spontaneous polarization. So, you can have very high 2 DEG sheet carrier density. That is how you are able to get very high power performance. These are the recent reports, and This is my group. Acknowledgement to all of them. They are involved in the development of this technology, be it material, be it device fabrication or characterization. Thank you very much.
Thank you for the nice talk. I have one question. You mentioned about CV characteristics of HEMT.
Yeah.
So it's a gate capacitance?
Yeah, it's a gate capacitance, and you basically when you vary your voltage and frequency, the capacitance CV curve varies depending on the position of the traps.
But why it is not done for low frequencies? Because 1 megahertz
Yeah,
also
it
high
is done for
frequency.
low frequencies also, but depending on the type of traps, you may or may not get effect on CV. So, if they are slow traps, you will get the effect on kilohertz range or low frequency. So, in our case, all are high frequency traps. So, we have shown it, although we have done for even low frequency also, but the effect was mainly seen for megahertz range. That is why I have shown it.
Okay, they are fast traps? It's
Yeah,
like,
they are fast traps.
Interface trap? It is.
Yes, interface. Okay. We have made both the kind of devices. Indigenous devices are carbon doped, and to qualify our process, we use imported wafers also. They are iron doped.
So the CV measurement?
CV measurement was on carbon doped. Yeah.
So you haven't tested the buffer free?
Buffer free not yet. We are just in the process of developing that. Yeah, because GaN is a well established company who is proposing this coin fine structure with buffer free. They are claiming that it is even better than the buffered one. So, that is how we are also going in that direction.
Concerning the thermal resistance of the transistor, do you measure it or?
We have done channel temperature measurement, and presently our channel temperature at operating 28 volt is around 150 degrees centigrade.
Long live India and France friendship.